we began with the notion of asymptotic flatness last time, and the idea here was that we got the physical space-time and so we changed the notation. So now the physical space-time is hatchet, and then conformal completion. And then this, where the definition of asymptotically flat spacetimes and asymptotically Minkowski spacetime. And the key points up here were that the field equations imply that Scri is null. And so the null normal to Scri, since omega, the conformal factor is constant, namely 0 on Scri, grad omega is normal to Scri, and therefore the null normal to Scri would be an A. So this at Scri is a null normal. So this is null. This null normal is a null vector field up here. The topology of Scri is S2 cross R. That is the one of the key points that we learned. And we saw that we can always go to a conformal frame in which grad A and B equal to 0 at Scri. So this is called the divergence-free conformal frame. And it's not essential, but it just simplifies all the calculations enormously. There's no loss of generality, and everything becomes rather elegant, and therefore one always uses this condition. And therefore we got on Scri in this frame, divergence grad A and B equal to 0, then we got the, well, in any case, we get the intrinsic metric on Scri, which is the pullback of the physical metric. This is signature 0 plus plus, and this is n is a null degenerate null direction, and this condition implies immediately that ln of QAB is also equal to 0. So all these equations are equations just hold at Scri, and this is what we are seeing. So now this is what we want to use, and we want to go ahead now and understand the physical properties of Scri. And so that is our next part up here, which is really other consequences. So we already used field equations a little bit, and we want to understand other consequences of field equations. And when I say field equations, of course, we just need field equations near Scri, asymptotic one. So this is what we're studying here, other consequences of field equations up here. And so by this we just mean that we're assumed that the physical stationary tensor has a property that limit to Scri of omega to the minus 2 times t hat AB this limit is smooth. That is to say the stationary tensor vanishes at some rate near Scri, and that is what we mean by field equations up here. So that's what we now want to understand. And in particular, we're going to see now the peeling properties. And as in the case of the Maxwell field, these peeling properties will enable us to sort of see which part of the curvature tensor carries information about radiation, which part is kind of freely specifiable, false like 1 upon R, that would carry the information of radiation, and then which part carries Coulombic information in terms of which mass can be expressed. In the case of Maxwell field, the Coulombic information was contained in phi10, and the integral of phi10 give a charge. So similarly, which field should we look at? That is a question that we want to understand. So the key point up here is the following, that we remember that the Riemann tensor can be expanded in terms of the Weyl tensor. And so we got Weyl tensor plus yes. This is called the Schouten tensor, and that is one that always appears in conformally invariant kind of analysis. So the wild tensor can be the Riemann tensor can be expanded like this. This is a fact that we saw in the early part of the course. So this is called the wild tensor. This is the curvature tensor or the Riemann tensor. And this, morally, this is just the Ricci tensor, because it is just the just some combination of the Ricci tensor. So now, the Ricci tensor we also know. Everybody can see here, right? No problem about seeing it here, Martin. Mm-hmm. So with the Ricci tensor in the conformally rescaled space-time up here is given by SAB plus twice omega. So this is just not as scribe. These equations hold everywhere in the neighborhood of scribe. Omega to the minus 1 times grad A. Grad A and B minus omega to the minus 2 times GAB and C and C. And this particular combination is just equal to the physical Schouten tensor or the physical Ricci tensor. And remember, because this is true, we know that that limit of omega to the minus 1 times SIAB to scribe is 0. Because omega to the minus 1 minus 2 times the stationary tensor side is smooth, so omega to the minus 1 times the stationary tensor is 0, and that means that the Ricci tensor, omega to the minus 1 times the Ricci tensor, physical Ricci tensor is 0, and therefore this particular combination is 0 up here. So we know that, and again, as before, N is everywhere. I'm just using notation here that NA is just grad A omega. This is a little bit confusing notation, but that has been in the literature all along. Namely, there is part of the literature, grad omega is called N. At scri, N is null, but grad omega is not null away from scri. So this is not a null vector, so this will not be by itself Newman-Penrose kind of tetrahedral vector, so we just keep in mind, but this is the notation. I could use another symbol up here, but since this is used very profusely in the literature, I will just call it grad A omega. Anytime there is a room for confusion, whether we're using a Newman-Penrose null vector or grad omega, I will make it completely clear. So what this tells us is that the physical, the conformally rescaled Schouten tensor is completely given by the physical Ricci tensor, which near scri is 0, or this goes to 0 at scri, and some other terms which are, so to say, kinematic in the sense that these other terms are just given by I mean, they're not trivial content, but nonetheless, they're just given by derivatives of omega, right? This is just derivatives of omega up here. Therefore, you would expect that kind of the crux, the leading order, the sort of the most important physical information will be contained in the wild tensor, because I've got the curvature tensor up here, and the SAB part is the physical SAB part, which goes to 0 at scri, plus some factors which just involve derivatives of conformal factor. So therefore, this is the thing that we had in mind up here. And now what we want to do is to work out consequences of this. Now, first of all, if I just look at, let's call this equation 1, this equation 2, and if I just look at the equation 2 up here, and if I multiply the equation 2 by omega squared, then omega squared times SAB is smooth, so at limit of this to square will be 0. If I multiply this by omega squared, there will be omega times grad B, so that term will go to 0. This will be just GAB, NA, and C and C. And then this of course goes to 0, because S hat itself goes to 0, therefore omega squared times that of course goes to 0. So that tells us immediately that at scra, GAB and C and C equal to 0, GAB is of course non-degenerate, and therefore N is null. That is what we had said already. But we already also actually use this equation to say that we can always choose a conformal factor such that grad A and B equal to 0. We can always do that. If I choose a conformal factor, grad A and B equal to 0, then we got some nice consequences. So this is general fact. This is just calculus, that if you had some function, some smooth function. At the moment, just for simplicity, this is not essential. I'm just assuming that everything is C infinity. Everything can be done with some Ck, where k is bigger than or equal to 3. Everything goes through. But then I will have to always tell you C3, that this is C3, this is C2, etc., etc. Whereas if I just assume everything is C infinity, if I take the derivative of a field which is C infinity, they are also C infinity. But what I should really do is to say that this function is C3, therefore its derivative is C2, etc. I'm just saving us trouble of saying those things. You can fill in those gaps if you wanted at some stage. So by smooth, I just mean C infinity, so that we don't have to worry about it. Or alternatively, has appropriate differentiability. So okay, that's what we do. So supposing you're given a smooth function f near sky, if you're given such a smooth function near sky, then we got some interesting things. And suppose f at sky's value is equal to 0. Now omega equal to 0 defines sky. Therefore, I can always do Taylor series expansion of this f near omega equal to 0, right? We can always do that. So that immediately says that if I do the Taylor series expansion, that immediately will tell me that that means that omega to the minus 1 times f is smooth. So if something vanishes, then in the Taylor series expansion, so if you like, in the Taylor series expansion of f up here, normally I'll get f at sky plus some derivative of df by d omega at sky times omega minus 0 times so omega equal to 0 at sky. So I'll get this plus there is some expansion up here. So since omega is equal to 0, I can just forget about it. Plus I'll get here d to f by d omega squared divided at sky times omega squared, etc., etc. So it's clear that if f is equal to 0, then omega to the minus 1 times f has a limit, and that limit is just dA by d omega. Since f is smooth, dA by d omega is smooth. If in fact omega minus 2 times f has a limit, that means that this is also 0, and then omega to the minus 2 times f is also smooth, because then it is given by this function, etc. So it's just to tell us an expansion, and this looks trivial, but it is very powerful. One uses it all the time. Okay. So here, in particular, what we know is, if I look at the equation 2, we are in a conformal frame, divergence-free conformal frame. Therefore, that divergence-free conformal frame just implies that grad A and B equal to 0 at sky. I use your functions, but of course the same thing is true for tensor fields, right? You just take the component of the tensor field in a chart which is well behaved in sky, which will be basically omega and coordinates of sky, u theta phi. In that, you do the Taylor series expansion, and then everything will be true. So this conformal frame implies this, and that implies that limit omega to the minus 1 times grad A and B is smooth at sky. So this is smooth as sky, this is smooth as sky, this actually is smooth and is 0 as sky. Therefore, that tells us that in fact n not only vanishes, the norm of n not only vanishes, but it vanishes like omega squared. Equal to omega squared times alpha, where this alpha is smooth. So it vanishes actually as omega squared. So that is going to have important consequences. So what I'm doing is it's really very simple. You know, we just had these two equations. One is just a definition of the Riemann tensor, and the other is a field equation. And using these equations, we're getting some important properties. So what am I driving at? What are the properties that we're going to get today? And we're going to get also more properties in the next week and the week after. But today, what we're driving at is really the properties which go under the name of peeling. Right? So in the Maxwell case, we obtain peeling by simply observing the conformal invariance of the Maxwell equation and making use of the fact, and assuming, if you like, that the FAB, the conformally rescaled Maxwell field, which is the same as physical Maxwell field, is smooth at scri. And after that, all the peeling properties of the physical Maxwell field just follow. Same thing, we want to do similar thing here, except that we know that Einstein's equations are not conformally invariant. This equation is not conformally invariant. And therefore, I cannot just assume that everything is as we wanted, as in everything is the same as in Maxwell's case, and therefore we have to do a little bit more work, and that is what we're getting at. So we're using the consequences of field equations to establish the peeling property. That is what we're going to do today. Okay. So we assume here, so we find here that in fact n vanishes as omega squared and not just as omega. So now what we can do is, that's what we have, and therefore in this equation, therefore I can now replace this just by alpha times GAB, where alpha is smooth. Okay, so if I can just do that. And now what I can do is I can take a derivative of this equation and skew symmetrize. So what I'm going to do is the following. I'm going to take grad A. I multiply this equation first for omega and take the derivative of it. And when I do that, I multiply this by omega, therefore this omega goes away, plus twice and now here I'm going to get omega to the minus 2 times this, so I'm just going to get here. So this quantity is alpha, so I just get here alpha times omega times so I just get this equation, and now I use the fact that this is just the Riemann tensor. This is just the Riemann tensor here, and I use 1. And then I simplify, in other words, I use 1, so I'll get again S is up here, I already have S coming from here, so you simplify various terms. And then when so you use that, so this is equal to use 1, and therefore I simplify. It is straightforward algebra, so you just do that, and when you do that, you obtain the two equations. The first equation that you will see is SAB times NB is proportional to NB. So SAB times NB is equal to alpha is equal to minus alpha. The same alpha that we got up here. And we also, so first that is the conclusion, and then we also find another consequence of this, and the consequence of this is just equal to omega times. And now is equal to something that involves this as hat AB, so that is just going to be equal to grad A of omega times T. I just now again use Einstein's equation to express S in terms of T, and you will get that. It doesn't matter because this term is anyway 0. In the limit, this term will be the 0 because T itself is 0, and this omega times T, so it's good. So this vanishes at omega, this is another omega, so I get omega squared. So even if I take the derivative, the limit of this is going to be 0 in the limit. So in the limit, therefore, this is going to go to 0 at scri. This is going to 0 at scri, because I got omega sitting up here, and this is smooth, so omega up here. So that, therefore, I conclude that that CD times ND is equal to 0 at scri. So this is an important conclusion that we got, and just came from the field equations. The algebra is really straightforward. You can all do it in between 15 minutes and half an hour, depending on how facile you are with this tensor calculations. But the point is that using asymptotic flatness, that is to say conditions there on the sky, and using the field equations, we come to the conclusion that wild tensor is extremely, the rescale wild tensor is extremely restricted, namely that this quantity dotted with n, where n is a null normal to sky, is actually equal to 0. Now this is very different from what we had seen for the Maxwell field, right? For the Maxwell field was not rescale, confound rescale Maxwell field was not 0 at sky. So this is a key difference between spin 2 fields and spin 1 fields. Namely, normally one thinks of the Maxwell field as being the electromagnetic analog of the wild tensor, because in source-free case, the only curvature in the Maxwell theory is FAB, and I mean there's no, FAB just satisfies curl of FAB equal to 0 and divergence of FAB equal to 0, and similarly wild tensor in absence of sources satisfies the appropriate equation, the Bianchi identities, which are like divergence of wild tensor equal to 0 and curl on 3 indices is equal to 0. So that is the wild tensor satisfies the equation grad M, grad A, C, A, B, C, D equal to 0, and grad A, C, B, C. They're like kind of like Maxwell's equations. There's some similarity between the source-free Maxwell's equation. And there are more indices, D, C, and D. If you like, the last 2 indices are going for a ride here. And because of this, and because in source-free case, the entire curvature is in FAB, and the entire curvature up here is in CABCD. And that is why one thinks the wild tensor as being analog of the Maxwell tensor for the spin 1 fields. But there's a big difference in the properties, asymptotic properties of these fields. In the spin 1 case, FAB is not 0 at sky, but in the spin 2 case, if you like, in the full general relativity and also in the linearized theory, you find that CABCD, we're not showing is equal to 0, but we're shown that CABCD and D is equal to 0. Now the point is that CABCD and D equal to 0, if sky were space-like, so for example, that is a case where positive cosmological constant or time-like, this condition CABCD and D equal to 0 would immediately imply that so if sky were space-like, then n is time-like. If sky were time-like, then n will be space-like. Okay. In our case is null, so I'm just making a side remark up here. Okay. If this were the case, then this immediately implies that the electric and the magnetic part of the wild tensor are 0. What is the electric part of the wild tensor? It is just given by Ca and Bn and the magnetic part of the wild tensor is just given by star Ca. Okay. And the analogy is, of course, that the electric field normally is just given by FAB and B, and magnetic field in Maxwell case is given by star FAB and B. In the Maxwell case, FAB has 6 components and E and B each has then 3 components. In our case, CABCD or CMBN has 10 components, wild tensor, and this is now going to be, say for example, it's described as space-like, then this will be a spatial tensor. In the lambda equal to 0 case, this is going to be a spatial tensor. Same thing is true here. It will be not spatial tensor, it will be a time-like tensor, but it's the same thing. It will be a spatial tensor and it is trace-free because C is trace-free. So this is called the electric part of the wild tensor, this is called the magnetic part of the wild tensor, if you have got a decomposition of the Y tensor using, if you like, in the space like in this case, you can think of n as being a time like normal. So if you like an observer, and given an observer world line, you can decompose the Y tensor into its electric part and its magnetic part. It is spatial and symmetric, and therefore it has 6 components, and trace-free removes 1 component, so it has 5 components. And B also has 5 components. And they together, they're independent, and they make the 10 components of the Y tensor. And you can, just from the definition, it's clear, if you just expand it out, that if in fact CA, B, C, D, and D equal to 0, then EAB equal to 0. Immediately imply that EAB equal to 0. And BAB is also 0, because BAB will be equal to epsilon AN PQ CPQ and then CPQ BN and then NN. So again, one of the C's, one of the N seeds C's, C, and then that is equal to 0, so that's also equal to 0. So the electric and magnetic parts are both 0 in this case, and therefore it would imply immediately that the Y tensor at scri would be equal to 0. So these are all equations at scri. So that will imply this is equal to 0, and that is equal to 0 at scri. Okay. So both in the de Sitter and the anti-de Sitter case, it follows immediately from the field equation that the Y tensor is 0, and this is a local calculation. We did not really use any global property of scri at all. Okay. But in the case of interest, so there's a remark up here. Now returning to null scri, now in this case again you can define the electric and magnetic part in this particular way. But because this is null, it turns out that the electric and magnetic parts are not independent. They share some components. The same thing is actually true in the case of Maxwell field. If n is time-like or space-like, then E and B are independent. If you know E and B, I can reconstruct F. But if n is null, then in fact, E always has 3 components up here. So it has 3 components, B again has 3 components, but it turns out that 3 of the components, it turns out that 2 of the components of EAB are actually shared. So 3 of the components of the electric field to begin with has 3 components. But if it is actually if n is null, then it turns out that 2 of these components are the same here and here. Only 1 component, so in other words, 2 of the components are the same, and therefore E and B do not suffice to determine FAB at all. There is in the null case, that is really a non-trivial statement that the electric and magnetic fields are not enough to actually determine the Maxwell field as a whole. Okay. Is everybody with me so far? I mean, it's just a fact about algebra of null vector fields. Namely, if you give me a 2 form and I plug into n, take the dual of that 2 form, plug into n, and then because if n is null, then there is some degeneracy, and therefore 2 of the components here are the same, third is not. Therefore, if you give me E and B, then I only get 4 components of this FAB, and 2 components in FAB are not determined. The same thing is true here. Namely, if in fact E and B, if in fact n is null, then these are not independent, and therefore they do not determine the Y tensor. Okay. It's not enough to determine the Y tensor at scri. So that is why even though we know that CAB, CD and D equal to 0, we cannot conclude CAB, CD equal to 0 in the case when there is no cosmological constant. If there were a cosmological constant, I can immediately conclude that in fact electric and magnetic parts are 0, therefore the Weyl tensor itself is 0. Is this clear? Are there any questions about this? I purposely went into a long song and dance because you'll hear about electric and magnetic part of the Weyl tensor very often, and you might wonder, well, why is it that if electric and magnetic parts are 0, then why isn't Weyl tensor not equal to 0? It is because electric and magnetic parts are 0 with respect to a null vector, not with respect to space-like or time-like vector. Yeah.
So, well, this is applied for gravitational waves.
Yeah,
like
so
for antimatter, I can imagine like the waves bounce back in a certain sense.
Yeah.
But for
So,
this, it will
yeah, so I think it will take a little while to see what it implies. So Weyl tensor is actually just 0 in both the sitter and the anti-de Sitter case up here. But we're about to see that in our case also, in the lambda equal to 0 case also, Weyl tensor is 0, but that requires an additional assumption, which is not needed up here. So we'll do that first, and then we can come back to the. So now we come to the but, or where in lambda equal to 0 case, one can use the topology and the key point up here is that we've got S2, not some other manifold. It's not R3, it's not torus cross R, but it's really S2 sphere cross R. It's because of S2 cross R, we will find that CAB, CD, and D equal to 0 does imply CAB, CD equal to 0. This is what I'll sketch the argument for. So I'm going into some detail about this because last time Sina asked, but isn't it true that peeling is just local? That peeling is a local property, it just follows from local equations, it has nothing to do with topology, and the answer is no. That is to say, it is no when asymptotically flat case that we are now considering. The answer is yes in the case of positive cosmological constant and negative cosmological constant. The peeling properties there will follow for any topology, but here the peeling properties are really going to follow only from for this topology, which is S2. I'm going to come to a peeling property in a second, but I just want to tell you why I'm giving you some details up here. So the topology restriction of Skra in the asymptotically flat case is not trivial. All right. So now, okay. So now, how does that follow? So I mean, I'll just give a sketch of proof. Again, just like what I did up here, I'll tell you what the main steps are. The main steps are the following: that you can first consider the tensor as epsilon ABC. This is the intrinsic alternating tensor. So for example, you can take epsilon ABC, defined to be equal to epsilon ABCD times LD. Think of it in Minkowski space LD at the moment. We're going to define LD in a minute, but there's an intrinsic tensor which can be defined like that. So therefore, we got 4 vectors, L, N, M, and M bar. If I hit with L, then that means the only time I'll get a non-zero contribution is if this L hits N. And therefore, the remaining quantities that I get up here, they are all going to be of the type LA, so proportional to some alpha times LA and B in bar C. So this is a side remark, just to give you intuition about the intrinsic alternating tensor on Sky. And what you can now do is, you can do epsilon ABC, epsilon MMP times C, AB, and N. So if I do that, I'll get some tensor, and I'm going to call that tensor just for lack of more symbol. Don't want to introduce another symbol, so I'll just call it script C. So I'm just going to use script C and P. And then this tensor CPC is, you can check that this is symmetric. and trace-free. I'm just stating it is something that you can check by explicitly using, for example, the tetrad vectors, which we're going to introduce in a minute. So it's symmetric and trace-free, and Bianchi identity that just implies that this tensor also satisfies dA of C equal to 0, and I can pull back this to scry. If I pull back this to scry, I obtain grad will pull back to some derivative operator scry, as we have seen in the case of the isolated horizons, and then I get here BC equal to 0. So this is true everywhere. I just apply it as scry, pull it back, and I will just obtain that in fact this satisfies this condition up here. And so I obtain a tensor field which is symmetric and trace-free and satisfies this particular condition. And of course by construction, it is such that, so actually I've written one more, symmetric and trace-free, and also CAB and B equal to 0. So it's also transverse. Yeah.
What is C with two lower indices?
This one?
The one on the low blow, where the delta A CBC equals 0. Where you pull back?
Oh. Thank you. Thank you. Both cases, this is the same tensor. Thank you. So Bianchi identity implies that. So what we have is we have a tensor field which is symmetric, trace-free, transverse. So this is C AB is symmetric, transverse, trace-free. Transverse just means perpendicular to N, and it's trace-free on scry, and satisfies this particular condition up here. And then there's just a simple theorem which I will not prove, but which is nothing to do with scry, nothing to do with anything. This is a theorem about two spheres that, in fact, if you have got such a tensor field which is symmetric, so on the two sphere, of course, the fact that this is NB just means that both these indices are tangential to the two sphere. So you can just think of this as being symmetric, trace-free, on the two sphere transverse to NA. And if you got a tensor field which is symmetric, trace-free, transverse, symmetric and trace-free on a two sphere and satisfy this condition, then C equals 0. This theorem critically uses the topology of S2. This theorem is not true, for example, if the topology were two torus. In the case of the two torus, for example, I can introduce, so if the topology were two torus, just for the side remark, then I can just take this CAB. So in the case of two torus, you can think of it as being just a two-dimensional flat rectangle with x and y, where this is identified and this is identified. That gives you a torus. This identification gives you S1. This identification gives you another S1, so you get S1 cross S1, that is two torus. And this is the x direction, and this is the y direction. And therefore, I can just take transverse traceless object to be, for example, CAB to be just equal to the unit x directional vector and y directional vector, if you like. This is like one of the two polarizations that we use for gravitational waves. Or I can use this to be equal to x hat A. Or I can use x hat A, x hat B minus y hat B. So this is symmetric and it's trace-free. Because if I take the trace, x and y are perpendicular. If I take the trace, I get 1 minus 1, that I get 0. And these are the two polarization tensors that you may have often seen for gravitational waves. But here we're just thinking of them as mathematical tensors up here. And so I clearly have these objects, and of course in this case on the torus is flat, so dAx hat b equals 0 is dA y hat b. So in fact, the derivative of CAB equals 0, so in particular, this condition is satisfied up here. So in the torus topology, there do exist transverse traceless tensor fields whose curl in this sense is equal to 0, and therefore I cannot conclude that this quantity is equal to 0. Okay, I cannot conclude this quantity. But in the case of in the case of Scry, in the case of the S2 topology, I can conclude this quantity is equal to 0. And now what I have to show you is, of course, that this quantity equal to 0, this does imply. So this is what I have to show. I'm not shown yet. This is what I would like to show. That I would like to show that this equal to 0 implies that the last component equal to 0. I did it in this way. I could have done it the other way. Namely, I could have put this part up here after understanding some algebraic properties of the tensor fields C, which satisfy CABCD equal to 0. So there are two steps, and I could have done them alternate ways. Here I chose to show that CABCD and D equal to 0 implies that that CPC is equal to 0, and now I want to show that CPC equal to 0 implies that in fact the whole Y tensor is equal to 0. So let's just do that now. So if you like, for the minute, think of all this as being a detour and come back to just CABCD and D equal to 0 as our conclusion. This is a conclusion that I got, and we want to understand what does this mean. How many components are 0 of the Y tensor? How many components are non-zero? That's what we would like to understand now. Okay. So let's come back to again this property, CABCD and D equal to 0, and understand its implications. Okay. And I'll come back to this blackboard up here in 1 minute. So if this is equal to 0, then what does it mean? So now what I can do is, it is convenient to introduce null tetrads, Newman Penrose. Okay. So what do we have? We got Scry, we got physical spacetime, and we got Scry. So yeah, at the moment it's just Scry plus, but for concreteness, I also draw Scry minus. I could have done the same construction as Scry minus. We just do it Scry plus up here. And what we have is we got a metric GAB. This is a conformal completion, and therefore I got a null normal to Scry. So I already have a vector which is null normal to Scry. And A at Scry is defined to be equal to GAB. Okay, so this is the null normal to Scry. Now what I do is I extend this vector field everywhere inside. As I construct a tetrad first of all. So to construct the tetrad on Scry, and then I'm going to extend it, I construct a tetrad on Scry as follows. Consider any cross section of Scry. So let's call it S0. S0 is any two-sphere cross section of Scry. Okay, I got S0 up here. And I'm going to label this cross section by some coordinate. So first I'm going to introduce an affine parameter of the vector field NA. Whereas a two-sphere cross section, then by definition this two-sphere cross section everywhere is transverse to NA. It's never tangential to NA. So this is going to be a space line. It is everywhere transverse to NA. And now I can use affine parameter on NA as follows. Affine parameter, of course, means grad NA u equal to 0. U is affine parameter. But I have to give the initial value. So I just choose this cross section and I say that u evaluated as naught is some constant, let's call it u naught. It's not a function of theta and phi, just a constant. And then I just have u equal to constant surfaces. So this is going to be equal to u equal to u naught. Then I'll get another cross section which will be equal to u equal to u1 and so on. These cross sections are just translated by the vector field u up here. So we get this coordinate u here. And of course I also have coordinates theta and phi here. And so I can just ask LA theta equal to 0, LA phi equal to 0, and therefore I obtain where I got coordinates u theta phi, where u is the affine parameter of n, and theta and phi are constant along every generator of Scri, along every integral curve of n. So I just get u theta phi, these are the coordinates. In Minkowski space, we started from the space-time interior and introduced these coordinates. Here, we're just looking at Scri by itself and constructing this Newman-Penrose type tetrad up here. So we're not there yet, but first I constructed some coordinates. And now I would like to introduce a Newman-Penrose type tetrads, and that is not the easy. You just take here LA to be a null vector, and I just take this null vector, adapt it to this cross section. So N was like that. So I take L to be the null vector which is future directed and also normal to this cross section. So this LA, so LA is normal to, is null, is the other null normal. Given any two sphere, there are exactly two null normals. I already have N, so I choose this. This is null. I chose it to be future directed. And LA is equal to -1. I just normalize it so that NA equal to -1. I already have N, so I just normalize it like that. And then I just take this L, N up here, and I can do either Ln of LA equal to 0. So if this would just imply that this is just NB cannot be LA minus NB cannot be LA. But since grad of n is equal to 0, it also is just parallel propagated. NB grad B LA equal to 0. So you can either take Ln or that. And similarly, I introduce two other vectors which are tangential to the cross section. I take two other vectors which are tangential to the cross section up here. So these vectors are going to be MA and M bar A. So I just take them, and so again I define on S naught a vectors MA and M bar A, which is complex, but they satisfy the null, but the M bar equal to 1, that's what we should before. And in fact, what I can just do is this, as in the case of Minkowski space, I can just define this to be equal to 1 upon square root of 2 times d by d theta. So this will be equal to d theta plus phi sine theta. So this is right. So I just define it like that. Then I will obtain a tetrad, a null tetrad. I obtain a tetrad on this cross section, and again just lead right them. And again, this is just equal to NB grad B of MA because the other term is equal to 0. So I can either lead drag them or parallel transport them along anyway. So on the one cross section, I got a tetrad, which is N, L, M, and M bar, and I lead drag them everywhere, so I'll get actually null tetrad on all of Scri. And now you can check very trivially that in fact that this LA is transverse, is null normal to all U equal to constant cross sections, and A and M bar A are tangent to all U equal to constant cross sections. So basically we got null vector fields L and M and M bar everywhere here, and everywhere I'm going to get M and M bar to be tangent to the cross section, and everywhere I'm going to get L to be the future directed normal, and such that an A and A and bar A, this is null vector. Okay. Just a word of caution. In Minkowski space, we started from space-time interior and then defined these tetrals, and therefore we got a vector field an A in Minkowski space, and this vector field an A in Minkowski space was square root of 2 times GAB, grad B omega in Minkowski space. So there was a square root of 2 factor. You have to keep track of the square root of 2 factor. From interior or from space-time, the square root of 2 is normal, is natural. If you come from scry, the square root of 2 is not natural, and therefore we just have to be careful. Consider the general framework. If you apply it to Minkowski space-time, make sure that you are distinguishing. This is the vector that we call n tilde A in Minkowski space. So you just make sure that when you compare it with Minkowski space, which vector you are talking about. Otherwise, you get factors of 2 or square root of 2 wrong, and that can be a pain in the neck. So this is a slight caution. But what we are doing right now is completely internally consistent. I just take this NA vector field, and then I construct LA and M and M bar, and then I get a null tetrad. And then finally, we can extend this off scry, this tetrad. By just asking, parallel transporting the tetrad along L. So we can ask that this be 0, we can ask that LA grad A and B be equal to 0, and this parallel transport, if you start with null tetrad, it again remains null, so in the neighborhood of scry, we get a tetrad NA, LA, NA, and bar. Okay. So what we did is we proceeded 2 steps. One is constructed a null tetrad on scry associated with the cross section, and then we just parallel transported it or lead dragged it along scry, and then we parallel transport the vector, the null tetrad that we got on scry inside along this LA, and I obtained such a null tetrad. So this is a null tetrad. This is a null tetrad with respect to GAB. So with respect to GAB, all of them are null, and with respect to GAB, the only scalar products which are not 0 are n dot L and M, which is -1, and M dot M bar, which is equal to +1. Okay, so we get this null tetrad. Okay, I know this is not my favorite way of doing things, but on the other hand, literature is full of these null tetrads. I don't introduce null tetrads in any of my work, if I can avoid it, but literature is full of that, and so I should introduce this for the sake of pedagogy so that you can read papers and so on. So we get this null tetrads up here, this lot of structure, and then we can look at with respect to physical space-time. We also have null tetrad. They are going to be equal to n hat A, L hat A, and n hat A and M bar hat A, such that G hat A B, N hat A, all null, and G hat A B, N hat A, N hat B. This is equal to -1, and G hat A B. um, m hat A, m bar hat B, plus 1, all are 0. And this null tetrad, not very surprising, is obtained from the conformally rescaled null tetrad just by conformal rescalings, as we did in Minkowski spacetime. So we just said n hat A equal to NA, L hat A to be equal to omega squared times LA, and m hat A to be equal to omega times NA. So these are the physically, this is just the way that the physical and the conformally rescaled null tetrads are related. This is exactly what we did in Minkowski spacetime, the rescaling between the physical null tetrad and the one in the conformally rescaled spacetime was just this. But in Minkowski spacetime, we had global coordinates r theta, t r theta phi. Then we went to u r theta phi and introduced these tetrads everywhere using those coordinates. In Kerr spacetimes, you don't have coordinates. So in fact, what we have is fundamentally these null tetrads, and we can introduce them because we can just start with scry. We do have scry, and there is a natural way to construct the null tetrad, and we extend them inside. And now, in terms of this null tetrad, we have got these Newman-Penrose components. So I can take CABCD and I can plug into it 2 n's and 2 m bars. And this is what we call, so this is called psi 4. We introduced this terminology already. This is called psi 4, except that, let me call it psi 4 under bar for a reason that will become clear in a minute. So psi 4 under bar, and then finally, this is what we had done when we did isolated horizons. We introduced all the null tetrads. So we got 4 null tetrads. Do people want me to write down all the 5 expressions, or just 2 will be enough? 2 is enough. And then we get here psi 0 bar. This under bar will be clear in a second. You just divide it equal to CABCD times I get here LA and B. So basically, as you go from psi 0 or psi 4 to psi 0, you're always flipping L and N, M bar and M and N bar. So N becomes L, M bar becomes M. So we just get that. And then in between, we got various other things. Now, what you will find is that if I look at these four components, psi 4, psi 3, psi 2, and psi 1, if I take these 4 components up here, then there is always one n. At least one n. In psi 3 and psi 4, there are 2 n's, and in psi 2 and psi 1, there is one n. So these are, but we saw that CABCD and D equal to 0. That's correct. So what this tells us is that at scry, in fact, psi 4 bar equal to 0, equal to psi 3 bar equal to psi 2 bar, psi 1 bar, that's scry equal to 0. So what is left is this component, psi 0. And it did not be 0 because there are 2 L's here. Because there is no n here. There are just L's, and there is no n here at all. And therefore, so what we had obtained here as a consequence of the field equation was the condition CABCD and D must vanish on scry. And what that condition tells us is that out of the 10 components of the Weyl tensor, in the null case, in the case when scry is null, or cosmological constant is 0, in fact, out of the 10 components, 8 components are 0, but these two complex, this complex component, that is the 2 real components, that need not be 0. So in the asymptotically flat case, Wild tensor a priori need not be 0 because this component may not be 0. However, the statement is that, so this equal to 0, this is the same as, now I write down in another color so that you can see the consequences. So I write this down. So this says that only psi 0 will be non-zero at stuff. So the field equations imply that everything should be 0 except perhaps psi 0. I don't know if psi 0 is 0 or not. However, if Scra has topology S2 cross R, and if all of the components are 0, if psi 4 is 0, psi 3 is 0, psi 2 is 0, psi 1 is 0, and the topology is S2 up here, then this psi 0 is very constrained. So the content of this psi 0, these are the components, this quantity up here is precisely psi 0. So basically, let me summarize now. I presented it in one way, now I want to present it the other way. The definition of the field equations imply that CAB, CD, and D equal to 0. Then in the terms of Newman-Penrose tetrars, that tells us that these components are all 0, but psi 0 cannot be 0. And I'm stuck. That's it. I cannot prove anything more if I just have local considerations. But if I have topology S2, then I can do more. Because these two components psi 0 are contained precisely in this traceless symmetric second rank tensor. This object is a tensor field on a 2-sphere. It is symmetric, so it has 3 components, and it is traceless, that removes 1, so it has 2 components. The 2 components of C in this Newman-Penrose tetrars, you can just work them out, by plugging here. Now you know what I mean by epsilon ABC. It is just given by epsilon ABCD times LD, where L is a Newman-Penrose tetra. So you can just plug in here, and you can check that this is really the same as psi 0. In fact, this is exactly the same as psi 0. So if I plug into it MC and MP, I will just get psi 0 up here. So this information is the same as psi 0. And what we now know from Bianchi identities is that this C tensor must satisfy this condition, or it's pulled back to Scra must satisfy this condition. And it's just a theorem that on a 2-sphere, if you have a tensor field which satisfies this symmetric trace-free tensor field which satisfies this condition, then the statement is that that tensor field is identical to 0. And therefore, we again know that this is equal to 0. To summarize, if I just have local considerations without a reference to any topology, and if the cosmological constant is positive or negative, I conclude that the Wild tensor is equal to 0. I Scra. But I do not have that conclusion in the case when cosmological constant is 0 and Scra is null. In that case, I only know that CAB, CD, and D equal to 0. But if in addition I know that the topology of Scra is S2 cross R, then the space of generators, the space of n vector fields, is a 2-sphere, then I can show that this remaining component, which is psi 0 in the Newman-Penrose language, is also identical to 0 because of Bianchi identity, and therefore I'm done. Therefore, the statement is that Wild tensor is 0. So, we are using this S2 cross R topology. This was the question that, as I said, Sina was asking me last time, and you see the answer in great detail here, namely that S2 cross R topology is essential to get this conclusion, which we are now going to use very strongly. So, the statement is that Scra S2 cross R, and as we just saw, if it was even compact, but torus topology, I could not conclude this. Then the asymptotic analysis would be quite different. But if it's S2 cross R, I can conclude this. And S2 cross R is physically, as I was saying last time in answer to Sina's question, is physically the obvious thing to look at, because these S2s are just the light fronts, going out from somewhere, and that they're going to be 2 spheres up here. So S2 cross R and field equations imply that Wild tensor is equal to 0. this is in big contrast to Maxwell theory. So a lot of things are very similar between Maxwell theory and general relativity. Those of you who know non-abelian theories, then if you consider Yang-Mills theories with a compact gauge group like SU2, for example, then the similarity with general relativity is even much higher, much closer. But there are differences, namely in Yang-Mills theory or in Maxwell's theory, FAB at scra is not equal to 0, and this in fact is the key field that we work with. But in Minkowski's, gravitation case, in fact, the Weyl tensor is equal to 0, and therefore the asymptotic Weyl tensor is not CABCD, but the asymptotic Weyl tensor is omega to the minus 1 times CABC. As we saw from just Taylor expansions or L'Hopital rule, if a tensor, smooth tensor field vanishes, then omega to the minus 1 times that tensor field has a smooth limit. So this is smooth, and this would define to be KABCD, and this is the asymptotic Weyl tensor. So it's just maybe it's a bit confusing to you because you might think that asymptotic Weyl tensor just means the Weyl tensor evaluated at infinity. No, there is omega to the minus 1 factor there that complicates life often or simplifies life that we have to always keep into account. So this is what we mean by asymptotic Weyl tensor. Now KABCD is smooth. That implies that if I now define psi 4, so that's why I put psi 4 bar here, because I was using CABCD. So this bar was just because of the CABCD, and these quantities are 0. Therefore now, if I by psi 4, I just define to be equal to KABCD times NA, N bar B, and C, N bar D. So the same definitions, but instead of C, I'm using K, psi 0 to be equal to KABCD LA, NB, NC, and D. Same thing, but except with KABCD. Then the statement is that these are all smooth, and in general, they are not vanishing. Of course, in specific solutions, some of them may vanish, but in general, they are not vanishing. So these are the asymptotic Weyl tensor, and these are smooth up here. But just on this board, we have the relation between the physical tetras and the real tetras. Therefore, we can now go to the physical space-time and see what the fall-off is. So you just have to use two facts, or maybe we'll just do it next time. So this is smooth, so this will going to imply healing properties in physical space. So we'll get these peeling properties of the physical space-time Weyl tensor, and that will, as in the Maxwell case, we'll see that those peeling properties suggest strongly that psi 4, its value at scra plus, is a radiation field. And that is what people plot when they talk about gravitational waves. You have seen 100,000 times by now, I think, the waveform. And when people are plotting waveform, that waveform has been computed first using psi 4 and then integrating it twice, as I will explain later. But it's basically psi 4 that one is plotting up here. And then we've got psi 3, and then there is an in-between thing, which is going to be equal to psi 2, which we'll write down explicitly next time. And this psi 2 is going to have Coulombic information. So the mass will be constructed on this psi 2. And the positive mass theory that you heard about refer to the psi 2, and psi 4 will be the radiation field. And this is very similar to what happened in the Maxwell case. In the Maxwell case, we had got phi 2, that was equal to FAB times 1n bar. And that was the radiation field. And then instead of psi 2, we had got phi 1, and that was FAB times LA and B plus bar B. And this have the Coulombic information. So the middle one, in the Maxwell case, where there are phi 2, phi 1, phi 0. The middle one is Coulombic information, and the one at the end with two n's is a radiation field. With n is a radiation field, whereas in the wild tensor, the one with two n's is a radiation field, and again the middle one is really the Coulombic information. This is what we're going to see next time, and then we're going to develop all these things starting from there. So we use field equations and the topology to arrive at some peeling properties of the wild tensor in Minkowski spacetime, and that is telling us some physics. That is the point of today's talk.